So, dear students, today we are going to start a new topic in the subject on analog and digital communication, and that new topic is noise. And this topic of noise is very, very important for any communication engineer because there is no communication system which does not have to deal with noise. So, we need to understand what noise is, how noise affects our communication system, and how do we deal with noise, or how do we try to analyze noise on paper. So if we are able to understand noise completely, then we can find various ways, or we can devise means to combat the noise. So let us now move forward. So students, first we need to know what is the meaning of noise. We all know noise is something which is disturbing, whether it is in our day-to-day life or in our subject on communication engineering. So noise is an unwanted form of energy if we talk in terms of electrical signals or electrical communication system. So noise, it tends to interfere with the proper reception and the reproduction of the transmitted signal. Okay, so students, we also face noise in our day-to-day communication. In our day-to-day, you can say talk, if there is some noise, we are not able to concentrate on the job we are doing. If we have a noise, we cannot communicate our things properly from one place to another place. So same is the case here. In case of our electrical transmitted signal, our noise interfere with the proper reception and the reproduction of the transmitted signal. So here you must notice the word receiver here. So let me tell you one thing very important here, that noise has the greatest role at receiver side. You all know that in case of any communication system, we have transmitter and we have receiver. So since we transmit from the receiver, so transmitted signal is in our hands. You can say transmitted signal is the original signal. Okay. And noise enters into our communication system when our signal is launched into the channel or in the medium. So you can see in the block diagram at the bottom of this slide that once our signal is launched into the channel, then noise is introduced into our transmitted signal. So you can see here that the noise sources, they are generating noise, and noise is superimposed onto the transmitted signal in the channel. So who has to deal with the noise? It is the receiver who has to deal with the noise. Okay, so receiver has to do two things. One thing is he has to extract, or he has to demodulate the transmitted signal or the original signal. That is one job of the receiver. Second job of the receiver is to remove noise. And added to that, the signal which is reaching from transmitter to receiver, the signal is reaching in a very weak state, because the signal has traveled all the way from transmitter to receiver through channel after traveling a long distance. So because of that, the strength of the signal which is reaching at the receiver side, it is very, very low. And added to that, noise is superimposed onto that low strength signal. Okay, so the job of the receiver is to identify, is to detect the weak signal, which is the desired one. And another job of the receiver is to extract that weak signal from so much noise which is present around. Okay, so dear student, it is the receiver whose job is the most critical in the presence of noise. So we have to make our receiver robust if we want to say that we want to combat the noise. Okay, so noise, it modifies our signal in unwanted way. Okay, obviously it is unwanted because it is not the desired one. Added to that, our noise modifies the signal in random way. Random means which is unpredictable. So noise is something whose behavior we cannot predict in advance. So that is another very important thing related to noise, that noise behaves in a random fashion. Noise is a random signal which superimposes our original signal. Okay, so when some random signal or unpredictable signal mixes with our original information signal, which is transmitted into the channel, then our signal becomes very complex. And due to this, the job of the receiver becomes further complex. Okay, so the biggest challenge for any communication engineer is to deal with noise. Apart from that, the biggest challenge for any communication engineer is to design such a receiver which can deal efficiently with the noise. Dealing efficiently with the noise means our receiver should be immune against noise, or our receiver should be able to reject noise. That is the main job of receiver. I hope now you can appreciate the fact that the maximum energy of any communication engineer, it is spent in designing the receiver only. That's why you must have noticed this thing whenever you study any subject on communication, that most of the coverage, most of the emphasis is given on the receiver part only, because that is the most important one, and obviously the most crucial one, where uh, reception of your information signal is feasible. Okay, apart from that, the noise is ever present. It doesn't happen that for some period of time noise is not present at all. It's not possible. Okay, and noise limits the performance of the communication system when it is present in the pass band of the receiver. So this is another point that you need to understand here. Pass band of the receiver means your noise is present everywhere, and noise is present over most of the bandwidth which is available in the wireless channel. Okay, but we are allocating a specific amount of bandwidth to a particular receiver. So obviously the noise frequencies which will be coming into the pass band, or which will be coming within the bandwidth of that receiver, only that noise will affect us. Okay, so when we filter our signal for the desired bandwidth, noise also is also filtered, and noise enters into along with the signal within that bandwidth only. Okay, so we have to take into consideration the bandwidth of the, or the pass bandwidth of the receiver also, along with noise amplitude. Okay, and you can see here in the slide also that I have provided a rough representation of noise signal. You can see here that nothing is seems to be predictable here, and it seems to be that this signal is totally random in nature. So this is how your noise look like. And when we talked about modulation, though our modulating signal is also unpredictable, but it is not that random as your noise is, or it's not that unwanted as your noise is. Okay, so I hope you are able to appreciate the concept of noise here. Next. So as I told you few effects of noise in the previous slide. So your noise, it also limits the range of communication system. So that is very obvious, because noise limits the performance of communication system. It makes the reception of communication signal difficult. So that's why, because of noise, your signal may not be able to transmit itself from one place to another place in a better fashion. Okay, so for a given transmitted power, your range of the communication system, or means the distance for which your communication system is able to communicate, that may also become small. Okay, and as I told you that your noise affects the reception of weak signal. Obviously at the input of the receiver we are receiving weak signals. That's why your noise affects adversely the reception of weak signal. Okay, so if you want to feel, or if you want to uh, assume or visualize that what kind of form a noise has, then you must have listened to AM radio, FM radio. So whenever we tune our AM radio or FM radio, till it is tuned, we hear some, some noise, some peculiar sound, or some hiss sound in the loudspeaker, in the radio receiver. So that hiss sound or those peculiar sounds, till we tune our AM receiver or FM receiver, that is nothing but an example of noise. Okay, you must have noticed snow. Confetti means colored snow in the TV picture, or your picture is not that clear many a times. So that is nothing but that is due to noise in the picture in the TV receiver. Okay, so in your radio receivers, in your TV receivers, we can very easily identify the presence of noise. That's why I have given you these examples here. Fine. Next, so we can broadly classify noise into two categories. One is external noise and another is internal noise. There are many classifications otherwise also. You once you read all those classification, you will be able to understand that. But broadly, we focus on two types of noise. One is external noise and another is internal noise. External noise means the noise which is generated due to sources external to the receiver. Means the noise generated external to the receiver. Receiver doesn't have any role in that. Okay. The next is internal noise, is that noise which is created within the receiver. Okay. Receiver components itself, they are generating noise. So that is the difference between external noise and internal noise. And in the coming slides, we will talk about external noise and internal noise in detail. Next. So now we discuss external noise. So students, external noise is generated from the sources which are external to the receiver. Okay. Another important point is it is difficult to treat external noise quantitatively. Students, you must know this thing, that noise is a random signal. But obviously, being communication engineer, we first analyze noise and its effect mathematically on paper. Okay, so once we analyze the type of noise and its effect on paper using some mathematical expressions or some other terms, we cannot design system. So that's why treating noise quantitatively or mathematically is very, very important. Okay, so the problem with external noise is it is very, very difficult to treat quantitatively. Okay, so you must have heard of satellite earth stations. You must have heard of radio telescopes. These earth stations and radio telescopes, they are located at very, very far away places from the hustle bustle of the city. And it is because these things are located in the noise free places, very remote places, where very less presence of noise is there. Almost noise free places are there where we locate our satellite earth stations and radio telescopes. Okay, I hope all of you have understood this thing. So there are mainly three types of external noise. One is atmospheric noise, second is extraterrestrial noise, and third is industrial noise. So from the name itself, you must have been able to guess the kind of external noise that we have, but there are few things that you may not know beforehand, and we need to discuss those with respect to external noise. So first, let us discuss what is atmospheric noise. So atmospheric noise means the noise which is generated from natural sources of disturbances. Okay, now what are those natural sources of disturbances? Those natural sources are thunderstorms and other electric disturbances in the atmosphere. Okay, so students, mind here the words electric disturbances. When I say noise, this noise doesn't mean that the noise, the way we describe noise in our day to day life. By noise, I don't want to say that some disturbance that we get from music or something. Otherwise, here I am mainly concerned with the electrical noise. Okay, so the atmospheric noise, which is in the form of electrical signal or electrical noise signal. So that's why if you look into the natural sources of disturbances, I have taken those sources, or I have considered those sources which have the possibility of introducing electrical noise through atmosphere. Okay, and you can very well fully see that your thunderstorms, they provide, or they are a source of electric disturbances, and other sources also in the atmosphere which causes electrical noise. Okay, and these sources of external noise, they induce voltages in the antenna. So obviously, if we have a receiver, in that receiver we have an antenna. So obviously the job of the antenna is to convert your radio frequency signal into electrical signal. Okay, so the radio waves which are present in the atmosphere, okay, due to some natural sources of disturbances, okay, those radio waves, those spurious radio waves, they induce voltages in the antenna, and those voltages then interfere with our desired signal. And we call these induced voltages from radio waves, spurious radio waves in the atmosphere, we call that as atmospheric noise. Okay, another name for atmospheric noise is static. Okay, one thing. Another thing is, as I told you in the introduction to noise, that bandwidth is also very, very important part in noise. So this external noise is spread over most of the RF spectrum. RF means radio frequency spectrum. So whatever radio frequency spectrum we have, your external noise is spread over the entire spectrum. It doesn't mean that it is limited to certain range of frequency. It is present over entire frequency range. Okay, and these atmospheric noise is present in the form of impulses, and the field strength of these impulses is proportional to the frequency. That means at lower frequency, the field strength of atmospheric noise is much higher as compared to high frequency. So that's why your atmospheric noise is more prominent at frequencies less than 30 megahertz. And if your frequency is more than 30 megahertz, in that case, your atmospheric noise becomes less severe. I don't say that atmospheric noise is eliminated. It is present uniformly throughout the RF spectrum, but it becomes less severe at frequencies greater than 30 megahertz. I hope all of you have been able to understand. Next. Next is extraterrestrial noise. So this extraterrestrial noise, it consists of two types of noise. One is your solar noise and another is your cosmic noise. We all know solar noise means the noise generated from or generated through sun. And we all know that noise is such a big source of energy which generates so many types of radiations. Okay, so our sun generates constant noise radiations due to its high temperature. Okay, and those radiations which are generated from the sun, they are also over very broad frequency spectrum, and it also includes the frequencies that we use for communication. So obviously we know that sun undergoes a lot of cycles, and under those cycles the intensity of the radiations generated from sun, it keeps on varying. So sun is also a very big source of noise radiation. Then next is your cosmic noise. Cosmic noise means the noise generated from other distant stars and galaxies. We know sun is also a star, the most prominent star. And apart from that, we have many more distant stars and galaxies. Our Milky Way is our own galaxy. So all these stars and galaxy also generate noise. Fine. So radio frequency noise radiations, they are generated as cosmic noise, and we call cosmic noise as thermal noise or black body noise also. Okay, so the noise which comes from your extraterrestrial bodies or from the space, those noise frequencies are observable at the frequencies in the range from 8 megahertz to 1.43 megahertz. So these frequency ranges you must notice, students, and keep in mind and remember these values. Next is industrial noise. So as I told you in the atmospheric noise, that we are mainly concerned with the electrical kind of atmospheric noise. So same applies to industrial noise also. We have sound pollution or noise related to sound also, but we are not concerned with that. We are mainly concerned with electrical natured noise. Okay, so in the industrial noise, we are concerned with the noise which is generated from the sources like ignition, due to ignition in the automobile and aircraft, the noise which is generated from the electric motors, from the switching equipment, and from the high voltage lines leakage, okay, and heavy electric machines. So students, you must have been aware of the fact that, like, whenever we do ignition in our engines, even in our cars, when we start our car, there is some electric discharge. Okay, and that electric discharge, if you have turned on am in your car, and if you start your engine, or you ignite your engine, in that case some disturbance is observed in that am radio. Okay, so same is the case, like if you have used or if you have seen older tube lights where we used to have our chalk. Okay, and when we turn on that tube light and some radio receiver is on in your house, then obviously some disturbance is felt there. Okay, so because of these electric discharge or electric spark, we get noise. Okay, so another source of industrial noise is the fluorescent lights. They also affect the sensitive receiver reception. So if your receiver is sensitive enough, it will get the disturbance or the noise from the fluorescent lights also. Okay, since in case of your industrial noise, the sources in industrial noise, they range from very small kind of source to very big source of industrial noise. So the nature of industrial noise is highly variable. Okay, but one thing you should notice here, that uh, industrial noise is generated from so many sources which involve some kind of electric spark, or you can say arc discharge. Okay, so I hope you are able to appreciate the sources of industrial noise. Next. So after we have discussed sources of external noise, now we will talk about internal noise. I told you that in internal noise, the noise is generated within the receiver. Obviously, what do we have in the receiver? We have certain electronic components in the receiver. Also, we have some electrical component in the receiver. So the noise created by those components, that constitutes internal noise. Okay, we have many active devices in the receiver, we have many passive devices in the receiver, all are source of internal noise. Okay, and we need to know where does that noise come from. Okay, so obviously that kind of noise we will discuss in the next slide. We have three kind of internal noise. One is thermal agitation noise, another is short noise, and third is transit time noise. But before we move to those types of noise, we should talk about one or two general conceptual thing related to internal noise. So as I told you, in case of external noise, that your external noise nature is difficult to predict, and it could not be quantified. Means we could not represent easily our external noise with the help of some mathematical expression. Whereas in case of internal noise, our internal noise is easy to observe. Apart from that, we can describe our internal noise statistically. Means statistically means mathematically. Okay, so we can quantify our internal noise statistically or mathematically. So this is very, very important point. Students, from the very beginning of this subject on analog and digital communication, I am telling you that without mathematics we cannot understand communication. So here also I want to tell you that unless we are able to represent our noise mathematically, we cannot understand its effect, or we cannot understand its behavior along with your communication system. So here, or in the performance of communication system, what we will do, we will represent our noise mathematically or statistically. Okay, or you can say we will be modeling our noise mathematically, and we will apply that mathematical representation of noise onto our mathematical model of our signal, and then we will try to observe the effect of noise onto the signal. Okay, and as I told you that noise is totally random, so same is the case with internal noise as well. It is our random, and we cannot uh, treat noise on individual voltage basis or instantaneous value basis. So that's why we consider noise statistically, where we have averages, we have mean, we have mean square value, we have mean cube value, means statistical averages. You must have heard of first moment, second moment. All of you have studied statistics in your initial classes. Okay, so this is very, very important point, that we will be representing our noise mathematically with the help of statistical parameters. Okay, and in terms of bandwidth, if I talk about that, this internal noise is also randomly distributed over entire radio spectrum. Okay, and this random noise is proportional to the bandwidth over which it is measured. So very true, if the bandwidth over which the noise is measured, it is large, then obviously more noise will be entered in our system, and noise power will also be high. And if we have small bandwidth for the noise, then noise power will also be small. Okay, so after we have talked about the main concepts of internal noise, now let us move to one of the types of internal noise, that is thermal agitation noise. So what do we understand by thermal agitation noise? Means noise which is generated due to thermal agitation. We all know that every material is made up of atoms and molecules, and every atom or molecule has its own internal kinetic energy. We know that if the temperature of atom or molecule is more than 0 degree, is more than 0 degree Kelvin, in that case there is some kinetic energy associated in your molecules and atom. Okay, and because of that kinetic energy, there is some thermal energy present into your atom and molecule. Okay, so this thermal agitation noise is due to rapid and random motion of molecules. We know your molecules are not static, they are under continuous motion, which is random as well as rapid. Okay, so this thermal agitation noise is due to the random motion of molecules inside the components. Okay, another name for this thermal agitation noise is Johnson noise. Fine. So how do we now mathematically define this thermal agitation noise? Okay, we all know, as I told you, that this thermal agitation noise is internal noise, which is due to the active or passive components present in the circuit. So here we consider the noise generated by a resistance or resistor, a simple resistor. Okay, so as we have talked about in previous slide also, that your noise power is represented by Pn here. It is proportional to the bandwidth over which it is measured. And here the noise generated by the resistor is also proportional to the temperature of that material. Okay, so your noise power is proportional to both temperature as well as the bandwidth over which your noise is measured. And if we remove this proportionality constant, we get noise power equal to kT delta F. Your K is Boltzmann constant. You all know what is Boltzmann constant. Its value is 1.38 into 10 to the minus 23 joule per Kelvin. Okay, your T is your absolute temperature in degree Kelvin. Okay, and delta F is your bandwidth. So noise generated by a resistor is Pn is equal to K times T delta F. Okay, another important thing that you need to notice here is that, as I told you, that your generated noise is random. Okay, so obviously some voltage will be associated with that generated noise, and that voltage will be having finite RMS value. So students, this noise that we will be discussing or generating in our present lecture, all the noise voltages, they will be RMS values, not the instantaneous values. Fine. So let us now represent our noise generation through resistor in the form of some equivalent circuit. Okay, so this is the equivalent circuit where we are saying that this Vn is the noise voltage source. Okay, and R is the resistor which is generating noise. Okay, so we are representing our resistor, equivalent circuit of the resistor, which is generating a noise, as a voltage source with voltage Vn having resistance R in series. Okay, and what we are assuming here, that this noise voltage which is generated by this resistance R is completely transferred to this resistance RL. Okay, so RL is some load resistance. Though this RL is also resistance, obviously it will also have some its own noise, but we are assuming that this load resistance is noiseless resistor, so that we can say that whatever noise has been noticed across RL, it is only and only from R. Okay, so we have assumed that our RL is noiseless. Okay, then Vn is our equivalent noise voltage. Fine, and R is the resistor which is generating noise. Fine, so now what we want maximum noise which is generated by R to be transmitted across RL. So we all know what is maximum power transfer theorem. So maximum power will be transferred when your RL is equal to R. Your load resistance is equal to your source resistance. If both are equal, then we say that maximum power transfer will take place. Maximum power transfer taking place means the maximum noise generated by R will be transferred to RL. Okay, so this is our equivalent circuit of resistor. Now let us see. So as I told you that maximum noise power by R will be transferred to RL. We know that power is equal to V square by RL. V is the voltage, RL is our load resistance, and since because of maximum power transfer your RL is equal to R, so it becomes V square by R. Okay, and since R and RL due to maximum power transfer they are equal, so obviously in that case your V, that is voltage across RL, will be half of Vn. So your V is Vn by 2 whole square by R, and we get noise power is equal to Vn square by 4R. Okay, and from here we get Vn square is equal to 4R Pn, and we know the expression for Pn as we saw in the previous slide, that your Pn is equal to K times T delta F. So we substitute that and we get Vn square is equal to 4R KT delta F. And if you take under the root on both sides, you get Vn equal to under the root 4 KT delta F into R. which gives us the RMS noise voltage generated by resistor R. Okay, so R is the resistance, delta F is the bandwidth of interest, T is the absolute temperature, K is the Boltzmann constant, and 4 is a constant and under the root. Okay, so this is our RMS noise voltage due to R resistance. Okay, and if you take square of Vn, so this Vn square is proportional to what? Power. Fine. So as I told you in the previous slide also, that we will be considering RMS values instead of the instantaneous values. Fine. So here as a last line, I can say that your RMS noise voltage is proportional to the absolute temperature. It is also proportional to resistance value, and it is also proportional to the bandwidth over which noise is measured. I hope all of you have understood. Next. So other two types of internal noise include short noise and transit time noise. Okay, now first let us see what is short noise. Short noise means all of we know the working of our transistors and FETs. Okay, so whatever amplifying and active devices we have, we come across a short effect in that. Okay, so this short noise is generated due to short effect in all amplifying and active devices. Okay, and we know what happens in our BJTs and FETs. There is a, flow of electrons and flow of holes, and there is random variation in the arrival of electrons at various terminals of these FETs, BJTs, or you can say active devices or amplifying devices. So this short noise is caused due to random variation in the arrival of electrons. Okay, so in short noise, why do we call it short noise? Because it generates a kind of noise which appears like short. Okay, so this short noise is uh, represented in terms of equivalent short noise resistance. As I told you that your noise generated by a resistor uh, is proportional to the resistance value itself. So that's why your noise can also be represented in terms of equivalent resistance, and your active devices have equivalent short noise resistance present in their specification sheet. So I hope you can appreciate the significance of short noise in your active device or amplifying device. Fine. Next is your transit time noise. It is also associated with the flow of electron or related to traveling of electron from one terminal to another terminal. So we know that your electron travels from emitter to the collector in transistor. Okay, obviously as it travels from emitter to collector, it will take certain time. Okay, if that time taken by the electron, it becomes significant. Okay, then transit time noise will occur. Okay, and that time will become significant at high frequencies. Okay, obviously when frequencies are increased, then obviously uh, less time will be required to, or you can say will be expected from one terminal to another terminal. So in that case, this time taken by electron, it becomes comparable or significant at high frequencies. Okay, so in case of your transit time noise, at these higher frequencies, your noise input admittance of the transistor increases. So this is the effect of transit time noise. So these are two more types of internal noise. So with this, I have clarified you the concepts of external noise and internal noise, the main idea or the sources of these external noise and internal noise. How do we quantify them? I hope all of you have been able to understand the concept of external and internal noise. So students, after discussing the types of external and internal noise, now we move to noise calculation. How do we calculate different noise parameters? Okay, so one kind of calculation that we need with respect to noise is when we need to add the noise due to several sources. If we have several sources, how do we add the noise? So here we assume that there are two sources of thermal agitation. Okay, and these noise generators, they are in series, so obviously there are two sources. So your noise voltage due to source 1 is Vn1, noise voltage due to source 2 is Vn2. Okay, and the total noise voltage, it will be the uh, sum of squares of these noise voltage under the root. Okay, see, the way we treat RMS values, in the same way we have to treat these noise calculations. Okay, since my Vn1 is RMS noise voltage, so I am treating, in order to find the total voltage, it as accordingly. So a total noise voltage will be under the root Vn1 square plus Vn2 square. This is how we obtain noise due to several sources. If it is more than 2, that is 3 4, then we'll have Vn1 square plus Vn2 square plus Vn3 square and so on, and under the root. Okay, so we substitute value of Vn1 and Vn2, we get this. Okay, and your total resistance that we obtain here, that is equal to R1 plus R2 and so on. So in a way you can say here that your resistances, individual resistances, these are added. Okay, and the total noise voltage is caused by addition of these resistances and substituting in this general formula. That is one way. Another way is you obtain individual noise voltages, you square them, add them, and take the under root, and then you find out the total noise voltage. It is one and the same thing. Okay, so this is addition of noise due to several sources. Next. So how do we calculate noise when we have several amplifiers in cascade? That is also a very important point. Like if we have two amplifiers, one is amplifier having gain A1, another amplifier is having gain A2. Okay, so here R1 is the input resistance of amplifier 1, R2 is the resistance of amplifier 2, and R3 is the output resistance. Okay, and the noise voltages of individual you can say resistances is represented as Vn1, Vn2 and Vn3 respectively. Okay, so now here we need to add the noise generated by these individual resistances. So what method should we adopt so that we can calculate the noise resistance easily? Okay, so see, we have two amplifiers gain here in cascade, that is A1 and A2. So what is our objective here? Our objective is to find out equivalent noise resistance for the whole receiver. Means for this entire thing we want to find out equivalent noise resistance. So if we are able to do that, then it's a simple job. Okay, in the previous slide also we did that. What we are doing, we are finding out total resistance by simply adding the two resistances, three resistances, and then we substitute this total resistance in this formula. You can call this R total as equivalent resistance also. So same kind of thing here. For this entire schematic, we want to find out equivalent noise resistance for the whole receiver, that we can substitute and find out. So we will try to generalize this thing for many amplifiers in cascade. So how to do that? Let us see. So here we have first stage, which has input noise resistance R1, second stage as R2, and third as R3. Okay, we start from the output stage first. So here we have R3 resistance in series with your noise voltage Vn3, equivalent noise voltage. So Vn3 is under the root 4 kT delta F R3, the simple expression as we discussed in the previous slide. Let us see next. So this is the same expression I have reproduced here. Now what we want, that this R3 resistance, some noise voltage is generated here by this R3 resistance. Now what we want to have, I want to visualize the same effect of R3 at this point. Okay, but I want to assume that this R3 is present here instead of here. Okay, in another words, what I want to have is that I want to find out the noise voltage which would be present at the output if there were no R3. Okay, if I say that there is no R3, but I want same effect of R3 here. Okay, then how to do that? So if I want to remove R3, but I want same effect here, so I assume that R3 dash is present here. Some new resistance R3 dash is present here, and nothing of this kind is present. So because of R3 dash, the same effect of noise is coming here. I want to bring out that. Okay, so let us see that. So what is noise voltage Vn dash 3? That will be Vn3 by A2. Obviously, this is the gain of the amplifier. We know that as the signal travels, the gain is multiplied. So if we shift from this Vn3 voltage from output to the input side, obviously it will be divided by its gain. So Vn dash 3 will be equal to Vn3 by A2. Vn3 is, we have substituted its value, and now what we have done, we have taken this A2 inside this square root, and we get R3 dash. So if you look at this thing carefully, what is R3 dash? Let us see. So this R3 dash, if you take A2 inside this under the root, we get R3 dash equal to R3 by A2 square. Okay, fine. So what does it show? It shows that when a noise resistance, okay, when a noise resistance is transferred from the output of a stage to its input. So what we are doing, we are transferring this R3 from the output stage to the input. Okay, then what will happen? It must be divided by the square of the voltage gain of that stage. So your R3 dash is now R3 by A2 square. So A2 was the gain of this stage, and we have divided it by A2 square. Fine. This is regarding this. Now, this R3 dash is the new resistance that we have incorporated here. We already have R2 here. Now, what is the total resistance present now? This R2 plus the new resistance. So the total resistance, or you can say some equivalent resistance at this stage, is R equivalent dash equal to R2 plus R3 by A2 square. Okay, which is the summation of this R2 which is already present, and this R3 dash is the resistance which is obtained by referring output resistance back to input. Okay, so your R equivalent dash is equal to R2 plus R3 by A2 square. So in a way we have removed this R3, but we have obtained its effect by including the effect of gain of amplifier. Next. Now, once we have obtained the R equivalent dash resistance by R2 plus R3 dash, same kind of thing now we apply for this. Now what we say, that if we shift this set of resistance from output to input here, okay, so if we do that, this sum of resistances will also be divided by the gain of this stage, and the gain of this stage is nothing but your A1. So this is what has been done here, that your R dash equivalent, it has been divided by A1 square, and we get R2 dash. So this shifted to input side gives us R2 dash. Okay, R2 dash. And what is R2 dash? R equivalent dash upon A1 square. R equivalent dash we have already seen in the previous slide. This is our R equivalent dash. Okay, we substitute this thing. So we get this expression. If we solve it, we get R2 by A1 square plus R3 by A1 square plus A2 square. And at the input side, we have another resistance present, that is R1, which is as it is. So now the net resistance present at the input of these two amplifiers in cascade is R1 plus R2 dash. And we get the total equivalent resistance, which gives us R1 plus R2 by A1 square plus R3 by A1 square into A2 square. This is how we calculate the equivalent noise resistance of the whole cascaded amplifier. And this expression is quite clear just by looking at it. And whatsoever be the number of stages in any cascaded amplifier, we can find out the equivalent noise resistance expressed at the input of this cascaded amplifier. So see, R3 has been shifted twice. First at the input of A2 and then A1. So we have divided R3 by 2 times, A1 square, A2 square. R2 has been shifted only once. So R2 has been divided only by the A1 square. R1 has not been shifted at all. So it is R1. So this is how we can easily calculate the equivalent resistance in case of cascaded amplifier. Okay, so uh, I hope all of you have been able to understand this. Another important point that we need to notice here is that the noise resistance which is located at the input of the first stage, okay, at the input of the first stage means this resistance R1. So you can see here in this expression that R1 is having the highest value in the equivalent resistance. So it means R1 is the greatest contributor in R equivalent. So the noise or the resistance which is present at the input stage is the greatest contributor. As you move in the subsequent stages of the cascaded amplifier, your impact of those resistances in terms of for noise, it goes on decreasing. Okay, so this thing you need to remember, that noise resistance at the input of first stage is the greatest contributor to the total noise. Next. So next concept is noise figure. So before we move to noise figure, students, first we need to discuss signal to noise ratio, that is SNR. So this signal to noise ratio is very, very important thing in any communication system. We have talked about modulation technique, we have talked about demodulation technique, that is AM, FM, and we will also be studying many more modulation techniques. Okay, so signal to noise ratio is very, very important performance parameter for any communication system. Okay, so very frequently we will be coming across this parameter. We also call it as S by N or SNR. Okay, so this signal to noise ratio is very often used, very frequently used when equivalent noise resistance is difficult to obtain. So what we have done in the previous two methods, we have obtained equivalent noise resistances, whether it was your amplifiers in cascade, whether we had several noise sources present. Okay, in those cases we have obtained equivalent noise resistances. So where your equivalent noise resistance is difficult to obtain, we use SNR. So this SNR is the ratio of signal power to the noise power, and that too at the same point. This is very, very important. So your signal to noise ratio is obtained as the ratio of signal power to the noise power at the same point. Okay, and practically our effort is to keep this signal to noise ratio as high as possible or as high as practicable. The larger the value of signal to noise ratio, the better is the system. Okay, and this is quite understandable also. We want signal level to be as high as compared to your noise level. Obviously your signal level must be high as compared to your noise level. So mathematically we can express our signal to noise ratio as your signal power, that is Vs square by R, divided by noise power, that is Vn square by R. And if they are taken as the same point, obviously resistances will be cancelled and you get this Vs square by Vn square. This is your signal to noise ratio. Next, as I told you that our main emphasis in this is to discuss about noise figure. So your noise figure is derived from the signal to noise ratio itself. Noise figure is a parameter that quantifies noise. Okay, we define noise figure as the ratio of signal to noise ratio at the input to the signal to noise ratio at the output. So if we have a system, we will obtain SNR at the input. We can say this SNR as SNR I. Okay, then we will observe the SNR at the output of that system. We may represent that SNR as SNR naught. Okay, then the noise figure is defined as input SNR divided by output SNR. Okay, so this is how we define noise figure and it is represented by F. Okay, and why do we want this noise figure parameter? This noise figure parameter is very useful for comparing the performances of the receivers or amplifiers which are working at different impedance level. So if we have two receivers or two amplifiers whose input impedances are different, how will you compare their noise performance? So we can compare their noise performance by calculating their noise figure. Okay, so obviously what we want, obviously the signal to noise ratio at the input will always be higher than signal to noise ratio at the output, because as your signal travels from input to output, there is some degradation always possible. Okay, so at the maximum, the input SNR and output SNR, they can be equal at the maximum. So in that case, for an ideal receiver, so obviously that receiver will be ideal if the input SNR is transmitted as it is to the output side. In that case, the value of noise figure will be 1. So for the ideal case, noise figure value is 1. Okay, but for practical receiver, obviously there will be some degradation. In that case, your noise figure value will be greater than 1, meaning thereby that your input SNR will always be higher than your output SNR. And we can express our noise figure either as an actual ratio, or it can be expressed in dBs also. dBs you already know, it is decibels. Okay, so you can express your noise figure in decibels or as ratio. So students, after discussing the concept of noise figure, we need to discuss how to calculate noise figure. Okay, this is very important, because the calculation of noise figure is very important for using this noise figure practically. Okay, this is simple also. So let us now discuss the calculation of noise figure. So your noise figure will be calculated by treating your receiver. Okay, receiver or amplifier, or you can say some active device, whatever you are considering. The way we have discussed our two-port parameter, so in the same way your receiver or amplifier will be treated here. We will treat that receiver as 4-terminal network. So 2 terminal at the input side and 2 terminal at the output side. Okay, we assume that our input impedance is RT, our output impedance is RL. Okay, and the gain of the receiver or amplifier is A. Okay, so you see here that these are the This is our amplifier. This is our antenna. Obviously, since we have a receiver, so there will be antenna which will be inducing voltage due to radio wave coming from the space. Okay, and then this antenna voltage will be provided to this amplifier with gain A. Okay, and we have 4 terminals. These are the 2 terminals at the input of this amplifier, and these are the 2 output terminals. Okay, and the internal impedance of the antenna has been taken as Ra. Now, what are the steps for this noise figure calculation? So very simple. We have to determine the input signal power. We have to determine the input noise power. So from these two, we will be obtaining signal to noise ratio at the input. So this is what has been written here, input signal to noise ratio. Then we determine output signal power. Okay. Then we have output noise power. Okay, so sometimes it is not easy to measure determine mathematically the output noise power. In that case, we measure that, we observe that, and we take its value. Okay, so next step is, after we have obtained output noise power and output signal power, we get output signal to noise ratio. Fine. And then after obtaining both, we can obtain our noise figure as a ratio of input signal to noise ratio and output signal to noise ratio. Okay, so now let us see with the help of further mathematical analysis by taking the circuit that we have considered here, that how to obtain noise figure in this case. So let us see. So first, let us find out input signal voltage. Okay, so if you look at this input side carefully, we have Vn as the noise voltage, we have Vs as the signal voltage. See, you understand here, we have two signals at the input. Okay, one is noise voltage, noise signal, and the actual information signal. So your information signal or desired signal is represented, voltage is represented by Vs, and Vn is the noise voltage. Okay, so Vsi is the input signal voltage. Fine. So you see here your Ra and Rt, these are in series to this Vs. Okay, so obviously this volt, if we want to find out the voltage at the input, that is Vi, we'll have to apply voltage divider rule, and it is equal to Rt upon Rt plus Ra multiplied with Vs. So this is how we get input signal voltage. Then what will be input signal power? Input signal power will be V square by R. Okay, so if we do that, this is how we get input signal power. Now we need to determine input noise voltage. So your noise voltage is Vn. We already know how to express noise voltage in terms of your temperature and equivalent resistance. So we have Vn square equal to 4 kT delta F into R. That is the resistance across which your noise voltage is appearing. Fine. So here, if you see what is happening, if we want to find out this R is what? This R is some R equivalent across which the noise is present. Okay, and this is the circuit that we have. Okay, and what we want the equivalent noise resistance which is present in this input circuit. So if you apply Thevenin theorem, in that case we will short this voltage sources, and in that case your RT and RA, it will be parallel. So your Thevenin resistance will be nothing but this one, RA into RT divided by RA plus RT. So your R equivalent will be this Thevenin resistance. So if you substitute that, you get the input noise voltage. and this is voltage square. So this gives us the input noise power. So if you put these values, input noise power is VNI square. It will be not TI, it is wrongly written. It will be VNI square by RT. So if you substitute all these values, this is what do you get. So this is our input noise voltage, sorry, input noise power. So if you divide these two, that is PSI by PNI, we get input signal to noise ratio. And this is the expression that we get as input signal to noise ratio at the input side of this amplifier or this receiver. I hope all of you have understood this. Okay. So after obtaining input signal to noise ratio, now we will be calculating output signal to noise ratio. For that, we need output signal power and output noise power. So this is our output side. So output signal power will be output signal voltage square by RL, that is the output resistance. Okay. So if our input voltage is VSI, your output voltage will be gain times the input voltage, AVSI. So very simple. So if once we do that, we substitute the value of VSI from the previous expression. And if you solve it, this is what do you get as output signal power. Okay. Then as I told you that output noise power is not that simple to calculate. So here we assume that output noise power is nothing but P and not only. So your output signal to noise ratio will be PSO by PNO. And if you substitute, this is the final thing that you get as output signal to noise ratio. And finally, what we want noise figure. So noise figure is input signal to noise ratio by output signal to noise ratio. We substitute all the values here. And finally, this is what we get as output. We get as noise figure. Okay. That is input signal to noise ratio to the output signal to noise ratio. Fine. So this is how we calculate our noise figure. Now, as I told you in the previous two slides, that we can represent our noise in the form of equivalent resistance also. Okay. So if you express, if you want to express your noise figure in terms of equivalent resistance, okay, for the same circuit, we can write it like this, that your noise figure F is equal to 1 plus R dash equivalent by RA. And what is RA? RA is your antenna input antenna impedance. Okay. And what is R dash equivalent? R dash equivalent is the equivalent resistance of this thing. Fine. Okay. So but here one thing you have to remember, that this relationship will apply if and only if the conditions are mismatched. Mismatched condition means these R equivalent dash and RA, they are not equal. Because if they are equal, then maximum power transfer will take place under matched condition. So this expression is applicable only for the mismatched condition. This you have to memorize. Okay. And in most of the cases, it will be mismatched only. So then you can memorize the expression for noise figure as 1 plus R dash equivalent upon RA. Okay. Next. So students, after discussing the concept of noise figure and signal to noise ratio, we now will look into one more concept which is very, very important and crucial also, that is noise temperature. We have expressed our noise in terms of its equivalent resistance. We have measured the effect of noise in terms of signal to noise ratio. We have expressed noise in terms of noise figure also. Okay. In the noise figure also, we have expressed our noise figure in terms of SNR once and in terms of equivalent resistance in the last expression that we saw. So students, we can also express our noise in terms of noise temperature. Okay, so noise temperature is also one of the uh, you can say type of measures for noise. So in some of the cases, noise figure is also not the most convenient way of measuring noise. There noise temperature comes into picture. So though noise temperature is again having mathematical significance, which gives us the same kind of impact of noise as it actually exists. So noise temperature concept for noise performance is employed extensively in case of antennas, in case of low noise microwave amplifier. So as you study further in your semesters, in the coming semesters, or you can say in third year or final year of your B.Tech, you will study subjects like satellite communication, microwave communication. In those subjects, you will come across this concept of, or you can say use of noise temperature for calculating the effect of noise. So here you can just keep in your mind that noise temperature is extensively employed for antennas and low noise microwave amplifier. Fine. So the concept of noise temperature is additive, like noise power. Okay, the way if we want to find out total noise power, we add the power of individual sources. Similarly, in order to find out total noise, we can add the individual noise temperatures. Okay, another advantage of noise temperature is that the values of noise temperature for low noise levels. Okay, so these values of noise temperature, they show greater variations for any noise level change. So if there is any change in the noise level, actually noise level at very low noise level, then significant changes in noise temperature values are observed. So that's why smaller variation in the noise can also be noticed if you represent noise in terms of noise temperature. Okay, so we have already seen this thing, that if we have two noise sources, okay, then we can represent them by P1 and P2. Since your noise power is additive, so we can find out the total noise impact by adding these two. So P1 plus P2 becomes KT1 delta F plus K22 delta F. If we take K and delta F common, then we get T1 plus T2. So from here, your total noise voltage or your total noise power becomes proportional to the sum of your individual noise temperatures, or your total noise temperature is the sum of individual noise temperature, which shows that your noise temperature is additive for different noise sources. Okay, another thing is, if you remember in the previous slide, I had shown you this expression that noise figure in terms of equivalent resistances under mismatch condition can be shown like this. So same thing can also be replaced in terms of noise temperature. So your R equivalent can be shown proportional to equivalent temperature, and your RA is antenna resistance, can be shown as your equivalent temperature T naught. Okay, so your noise figure can be expressed in terms of equivalent temperature as 1 plus TQ upon T naught. And we already know that your noise power is proportional to your resistance. Your noise power is also proportional to the absolute temperature. Okay, so by taking that thing in consideration here, we have represented our noise figure in terms of equivalent noise temperature as well. Okay, so at some points you may come across noise temperature, which is nothing but the equivalent representation of noise. Okay, so your noise can be represented either in terms of equivalent resistance, it can be represented in terms of your signal to noise ratio, It can also be represented in terms of your noise figure. It can also be represented with the help of your noise temperature. So all these parameters, they take into consideration the noise itself as well as its effect. And these parameters help us in quantifying the noise in your electrical communication system. I hope all of you have understood this concept. Fine. Thank you. So that's all for today's class.